is that certain quantum field theories or quantum theories of gravity can be described fully by physics which lives on the boundary of the space-time which they live in. Okay. So in our case, the celestial amplitudes program aims to compute scattering amplitudes, which one would normally compute using Feynman diagrammatics and some bulk quantum field theory. The goal is to compute these scattering amplitudes using some theory which lives on the boundary of the space-time only. So none of the computations will have to do with Feynman diagrams. There's going to be nothing going on in the bulk. So that's kind of the aim of this. And it turns out, as we'll see, that the boundary theory ends up being a conformal field theory. And the correlation functions in the conformal field theory are the quantities which tell you about the S matrix elements, which one would compute using bulk techniques. And my goal over the next few days is to discuss certain properties of this so-called celestial conformal field theory. Now, the idea of celestial holography or celestial amplitudes, this idea has really only been around for maybe 5 or 6 years. It's a totally new phenomenon. So in this way, it's a very young field. However, the background was laid, depending on how you count, either something like 60 years ago or only 10. And what I mean by this is that there are these very old historic ideas in quantum field theory, things like soft theorems and asymptotic symmetries like this. But only in the last 10 years, they were understood in the context of one another. So maybe 10 years ago or so, Andy Strominger and his various collaborators were able to unify these seemingly disparate ideas when studying physics in asymptotically flat spacetimes. And this laid the seed for celestial holography. So this big, broad set of ideas, this is often called the infrared structure of gauge theories and gravity. And Andy actually wrote a book on this in 2017, which is a great book. And many treatments of celestial holography start by reviewing kind of what's in this book. They start by going over these historical developments which seeded the subject. This set of talks is going to be totally opposite to this philosophy. Rather, I'm going to cut straight to the chase. I'm going to talk about celestial amplitudes from essentially as quickly as I can. And we'll encounter some of these ideas about the infrared structure of gauge theory and gravity in due time. And the goal of doing it this way is to get you as quickly acquainted with the literature and able to read modern papers as fast as possible. And I hope by the end of these 3 talks, I will have succeeded in this mission. I know a lot of people, when they give introductory lectures on a subject, they promise that you'll be able to read the literature at the end of it. And we'll see how it goes for my set of talks. Hopefully I have the advantage that it's a relatively young field, so there's perhaps less to discuss than something rather more mature. Alrighty, so let's begin. The hero of our story is going to be the celestial sphere. So let me tell you what this is. So I'm going to begin by drawing the Penrose diagram for an arbitrary asymptotically flat space. And as you've perhaps seen before, it's just this diamond here. And let me mark a few points on this Penrose diagram, which gives you the conformal compactification of not just Minkowski space, but anything which is asymptotically flat. The first interesting points I want to mark are these future time like infinity and past time like infinity, which I mark I plus and I minus. And these points are interesting because the world line of all massive particles, remember massive particles have a time-like world line, hence the name time-like infinity. All massive particles always enter Minkowski space at past time-like infinity, and then they go on their trajectory, and then they exit Minkowski space at future time-like infinity. Okay? Where in this Penrose diagram, this is the time direction, and this is some radial direction. And at every point in the Penrose diagram sits a 2-dimensional sphere with radius given by this radial coordinate. So as you go farther towards the boundary, the radius of these spheres gets bigger and bigger. Okay. The next interesting point in this Penrose diagram is this I naught, which is called spatial infinity, and we won't have much to say about it here. But the hero of our story is actually going to be this null boundary, which is the conformal boundary for all asymptotically flat spacetimes. I'm going to label this conformal boundary scri plus for future null infinity and scri minus for past null infinity. Okay. Now, let me just focus on the case of scri plus for a moment. This conformal boundary has the topology of R across a two-sphere. The two spheres are essentially the same as these two spheres, which I was speaking about a moment ago, but now pushed all the way out to the boundary. And this R part is in reference to the fact that you can move along this boundary, okay? Now the coordinates on this boundary are given by U, Z, Z bar, where again, U is this coordinate which starts at -infinity over here. And as you move along the boundary, U gets progressively bigger and bigger. And Z and Z bar are complex coordinates on the Riemann sphere, which is this S2. And this Riemann sphere is actually the celestial sphere. Great. Okay. So unlike the case of time-like infinity, null infinity has the special property that all massless particles start at past null infinity, and as you track their world lines, they always end up at future null infinity. Okay? So the first key observation is that scattering amplitudes in the S matrix gives a map from Cauchy data on scram minus. Oh, whoops. So Cauchy data on past null infinity to Cauchy data on future null infinity. Let me explain why this is. So I'm going to be focusing on the case of massless particles alone. Although this can be generalized, it's easiest to just think of massless particles for the moment. Okay? And when you think of the S matrix normally, what do you have in mind? Well, you have a bunch of particles which enter your space-time at time equals -infinity, and they're very far separated in the far past. And then you send them into the bulk. They have some interactions in the bulk, maybe new particles are created or so forth, and then they scatter off. So in this way, the Cauchy data on scram minus is telling you what particles you're sending into, what particles you're scattering with, the incoming particles, and the Cauchy data on scram plus is what kind of particles you get out. So this would be how this is a very classical physics way to think about what the S matrix is. You have some Cauchy data. So this is at the level of classical physics. But already the thing that we observe here is that the S matrix is already a holographic object. And by this, what I mean is that to tell you everything you would like to know about the S matrix, all I need to do is specify degrees of freedom which live on the boundary of the space-time. I don't need to tell you about anything that's going on in the bulk. Specifying Cauchy data on the boundary is well enough to define everything about the S matrix. Okay? However, as I said earlier, when one wants to actually compute the S matrix, the normal thing that you do is you have some quantum field theory which lives in the bulk, and then you write down your Feynman rules, blah, blah, blah. And this is how one computes the S matrix in practice. Our mission today is to not do any of this, and rather to study this S matrix purely holographically, so purely as something which lives on this conformal boundary. Okay? Now, an unsung hero of our story is going to be the following. If P mu is a massless particle, then we'll parameterize it as follows. So we write P mu is equal to omega over 2, 1 plus z bar, z plus z bar, minus I z minus z bar, 1 minus z bar. Okay? So at this level, this is just a choice of how I want to parameterize my massless momenta. I could have chosen any old thing, but this will end up being very useful. It'll make the story much cleaner. And the claim is that P is massless, so P squared is equal to 0 for all choice of positive omega and for all pairs ZZ bar. So for any old thing, omega and ZZ bar, you'll find that this gives you a massless energy momentum vector. Now, the crucial observation is that not only do ZZ bar tell you about the parameterization of your momentum, the reason that this is so useful is because ZZ bar tell you the point on the celestial sphere and I'll write CS2 for celestial sphere, that a massless particle enters and exits. So what do I mean specifically by this? So recall that on the boundary, there's some sphere here, and the coordinates on the sphere are z bar. Now say I send a massless particle with this momentum here into the geometry, and I claim that it ends up at future null infinity. Well, what point on future null infinities does it end up at? And it's precisely the point z bar in these coordinates as the z bar that you use to parameterize the momentum. So this ties together one's parameterization for a null momentum with the point on the celestial sphere, which the particle with this null momentum exits the geometry. So the upshot is that we may view creation and annihilation operators so here I've just written some arbitrary annihilation operator for some particle in the quantum field theory, and I've written it in terms of this omega zz bar variables. So we may view this annihilation operator as being associated to a particular point on the celestial sphere. And that point is labeled precisely by the zz bar, which we use to parameterize the momentum. So here's our celestial sphere, and an annihilation operator can literally be thought of as something which lives at some point on the celestial sphere. Okay. Now, this allows us, please.
Usually when I think of calculating this, I don't have just null geodesics, I have plane waves.
Good, yeah.
But here, everything is just classical null trajectory.
No, very good. So at this level, it's classical. And at the level you're speaking of, that's a fantastic question. So if you have plane waves, then they go through the entire geometry like this. So they'll hit different values of u. All the u's from minus infinity to plus infinity are represented. But for whatever u coordinate they hit, they'll always hit at the same zz bar. So in this way, you're free to think of just one celestial sphere sitting at whatever point u you'd like. And when you scatter these plane waves, well, where will they hit this celestial sphere? They'll hit it at zz bar. Fair enough? Yeah, that's a great question. Something that that was something I didn't quite grapple with for a while. Okay, so the upshot is that one can write the S matrix in some holographic way, where you have certain operators which live on this celestial sphere at past null infinity. And the S matrix gives you a map to operators which live on the celestial sphere at future null infinity, where these operators are just the creation and annihilation operators. Okay. So let me make a few comments before we push on. The first comment I want to make is that we've only been talking about massless particles. The story totally generalizes to massive particles, but it's a bit more algebra to get there. So at the end of today's lecture, time permitting, I'm just going to state the results of how celestial holography works in the case of massive particles. But for the first bit of today, I just want you to think about massless particles alone. Now, the second comment I want to make is that implicitly here, when I parameterize this energy momentum vector, I've assumed that we live in 4 dimensions. Now, as string theorists, we're happy to relax this condition. And I claim that all the ideas of celestial holography carry over naturally to all bulk spacetime dimensions. And what I mean by this is that if you write this Penrose diagram for asymptotically flat d-dimensional space, then you find that it has precisely this structure. And now the celestial sphere has dimension d minus 2. So if I want to do celestial holography for some bulk 7-dimensional quantum field theory, then the boundary description would live on a 5-dimensional celestial sphere. And all the technology that I'll talk about today is freely holding in that situation. Okay, so now that we have this in mind, I'm going to tell you a little bit about 2D CFT. Are there any questions before I get into it? Great. All right. And just to remind you of some 2D CFT, I'm going to begin with the definition. The 2D global conformal group this is the group of globally defined holomorphic functions on the Riemann sphere. And this Riemann sphere is just going to be our celestial sphere. The algebra of this global conformal group is SO13, which is isomorphic at the level of Lie algebras to SL2C. Now, the fact that this algebra of the global conformal group in 2 dimensions is SO13 is going to be the heart of our story, because SO13 is also the Lorentz algebra of a 4D bulk theory. So this is going to play a crucial role. Now, the algebra is generated by the following 6 generators. We have L-1, L0, L+1, L-1 bar, L0 bar, and L+1 bar. And these generators satisfy the following algebra. Ln, Lm, this is equal to n minus m, Ln plus m. Similarly for the barred objects. And finally, the bars and the unbarred objects commute with one another. Okay. So this is the global conformal group in 2 dimensions and its algebra. Now there's also, I want to caution you, a notion of a local conformal group whose algebra is the Virasoro algebra. And in fact, when one usually studies conformal field theories in 2 dimensions, one has in mind a theory which satisfies this much larger symmetry algebra. Okay? Now we'll see tomorrow that our celestial conformal field theory indeed enjoys this full local conformal group and Virasoro algebra. However, for today, we're not going to be able to access this information until I tell you what the stress energy tensor for the theory is, and that'll come tomorrow. So I'm going to claim that our celestial CFT is ultimately going to satisfy this global conformal group today, and then we'll see its local enhancement tomorrow. Okay.
I mean, maybe you'll answer this tomorrow, but how much of this structure is going to necessitate the full Virasoro? Because that's what we'll be missing in other dimensions, right?
That's right. Very little, very little. Yeah, for what we'll see in other dimensions is that you have all this structure of global conformal primaries, which is what we have here. And it turns out in 2 dimensions, the global conformal primaries that I define in a moment will actually be Virasoro primaries. In higher dimensions, you obviously don't get this, but you don't need this. So it's fine. Okay.
What happened with the center of extension?
Good. So in 2 dimensions, it's a very good question. You'll find that the stress energy tensor, the way I'm going to define it tomorrow, has central charge C equals 0, which is odd and seemingly quite bad. However, one can add to this stress energy tensor that I'm going to define tomorrow a second term, which gives a central charge going as 1 over G Newton, which is much more familiar from ADS CFT. And the second term is related to some Sugawara construction of various currents in the CFT. But perhaps I'm getting a little bit ahead of myself if I try and describe something like that.
So in general, because of implementation.
That's right, yeah. Yeah. Okay, one more definition. A global conformal primary this is some operator which lives on the two sphere, and we'll say it has weights h and h bar. Oh. Sorry, give me a moment to fix my mic. A global conformal primary is defined by it having certain commutation relations with these generators, these L generators, okay? And what are these commutation relations? Well, with L minus one, a global conformal primary with weight HH bar, this is just the derivative. Yeah. And there are similar expressions for L naught and L1, which I'll actually write down in full detail, though it may bore you, because we will need this equation in about 10 minutes. So with L naught, it has the following commutation relation, where now we see this H parameter appearing, this weight. Okay. And finally, with L plus one, we have the following commutator. Z squared partial Z plus 2ZH HH bar. And for the, if you want to figure out the commutators with this barred elements of the algebra, then essentially you just put bars on everything over here. So instead of partial with respect to Z, it's partial with respect to Z bar. Instead of H, it's H bar, okay? And this is the definition of a global conformal primary in a 2D CFT. Another definition, if O is a global conformal primary defined in this way, then we say the dimension of O is given by this letter delta. Delta is just equal to H plus H bar. And we say that the spin of a conformal primary, this is just the difference of the words. Okay? So this is just a different way to parameterize the same information. You could write conformal primaries in terms of H and H bar, or you could write it in terms of their dimension and spin, and it'll be useful for us to be able to interchange between these two ideas. Okay. The next thing I want to talk about is this 4D Lorentz group. How this is actually equivalent to the 2D global conformal group. So I've alluded to this at the level of the algebra, they share the same algebra. Let me make this a little bit more specific.
When you discuss about the global conformal algebra, you mean that the parameter is under transformation, the infinitesimal parameter is just global or holomorphic?
That's right. That's right. Yeah. Yeah, that's right. That's right. So you don't allow it to have these singularities or poles or something like this. Okay. Let me give you a fact. The generators of the 4D Lorentz group they can be rewritten in terms of the 2D global conformal generators. So this shouldn't surprise you so far. At the level of the algebra, they're isomorphic, so one should be able to write the generators of one in terms of the other. The crucial part of this statement is that these new set of generators act naturally on operators living on the celestial sphere. And I'm going to discuss what this act naturally on the celestial sphere means. Okay, let me first show you what this isomorphism is, because it's useful to have a good understanding of it. So I'm going to write the generators of the 4D Lorentz group as mu nu, which is anti-symmetric in this mu nu indices. And I'm going to decompose them into two sets of 3 generators. The first set of 3 generators is the rotations. So I'm going to define Ji is equal to 1/2 epsilon ijk. This is a totally anti-symmetric tensor in 3 variables times mjk. Where this parameter I as well as jk, they're just 1, 2, and 3. So they're not 0 through 4, or 0 through 3 rather. And finally, we have the boosts. And we're going to write their generators ki. These are just m I0. Okay? And the claim is that the generators of the 2D conformal group can be rewritten in terms of these j's and k's in a way which satisfies the correct algebra. So specifically, I have in mind that L minus 1 is equal to 1/2 minus J1 plus I J2 plus I K1 plus K2. L naught is 1/2 J3 minus I K3. And L plus 1 is 1/2 J1 plus I J2 minus I K1 plus K2. So here are how you define the L generators. If you want to define the L bar generators, you just use the relation L bar n is equal to minus Ln, and you take, I guess, the adjoint here. So essentially, you put a minus sign in front of everything, and then you flip the signs in front of the i's when you take the adjoints. Okay. Now, an exercise is show that these satisfy the SL2 algebra. Okay. And what I mean by this is you know the commutation relations of the mu nus. They just satisfy the usual commutation relations of the Lorentz algebra. And if you plug them in here, and then you find that these L's and these L bars satisfy precisely the commutation relations that I gave here. Okay? So this is the part that should be unsurprising, because I've claimed that these algebras are isomorphic, and all I've done is show you the isomorphism. The more exciting thing is to talk about this act naturally on operators living on the celestial sphere business. Okay. And by the way, when I say exercise, I don't mean that this is something that you have to do. In this set of lectures, I'm going to say exercise a few times, and the reason is twofold. The first is that if you're interested in doing getting your hands dirty with some computations, this would be a good set of computations to get your hands dirty with. The second reason is because I don't want to get my hands dirty with these computations live on the blackboard in front of all you. So this is a way for me to just state some certain facts and tell you that they can be derived easily, but I'm not going to spend the time on the board doing the algebra. Okay, so that's the purpose of these exercises. Great. So now we're going to consider.
Maybe I have some simple questions. So in the SL2, you maybe have some primary stage, etc. You can define. How can I understand from the 4D point of view?
Yeah, this is a great question, and this will be kind of the purpose of the rest of this talk, in fact, to talk about the SL2 primary states in terms of operators living the 4D theory. Okay, so we're going to consider some annihilation operator, which again I'm going to parameterize in terms of this omega z bar variables. And we're going to assume for now that this is going to annihilate some scalar particle in the bulk quantum field theory. Though, of course, the story for spins is a straightforward generalization. Now, we have the following commutator. We know that the annihilation operator has this commutator with the Lorentz generators. This is equal to J mu nu AP, where this curly J mu nu is just equal to minus 2i P mu partial P nu minus P nu partial P mu. And the reason I'm going to focus on scalar operators is because when A has some spin, then one must also add some spinning term here in these commutation relations. But just for just to make our lives easier, we're going to forget about this and just treat scalars for a moment. Okay. Now, the first task is to rewrite the angular momentum in terms of this omega zz bar variables. So specifically, I've given this angular momentum operator to you in terms of P naught, P1, P2, and P3. But I've told you how the components of this vector are related to omega, z, and z bar. So you can just do the change of variables and look at some Jacobians and figure out precisely what this operator looks like in terms of this new set of variables. So for example, one finds the following. That the commutator with M 03, this is given by Iz partial z plus z bar partial z bar minus omega partial omega acting on this annihilation operator. Okay, so this is just one example, but you have to do this for all these mu nus, which again, I'll leave that as an exercise. Okay, so this is how these commutation relations look like in this new set of variables, which is more convenient. And now we get to the main punchline of the story. And the punchline of the story is, say you want to compute the commutation relations with these LNs and this annihilation operator. Well, what you should do is it's kind of a straightforward, if algebraically tedious thing. First, you need to compute how the annihilation operator commutes with all the mu nus. And then you need to package these mu nus in terms of the various rotations and boosts. Okay, the next thing is to write these newly repackaged operators in terms of the LNs. And from there, you have all the ingredients that you need to compute the commutator between the LNs and these annihilation operators. Now, doing all this tedious algebra, one finds the following very pleasing results. Okay. This commutator is precisely this expression. The commutator with L naught is precisely 2z partial z minus omega d omega. And the final commutator with L plus 1 is given by this expression. And finally, if you want to compute the commutators with these L bars, all you need to do is you need to swap z and z bar. Okay, so that's how the L bar commutators work. It should be pretty clear that these two things are very similar to one another. So the definition for a global conformal primary with weights h and h bar, this is their definition. And we find that these annihilation operators have precisely these commutation relations, which are incredibly similar. So they're very suggestive in this way. And the observation is that A omega ZZ bar this resembles a global conformal primary with conformal dimension delta is minus omega partial omega, and the spin of this operator is just 0, okay? So one can see that if one puts omega partial omega is equal to 2h, then you get precisely this statement. So A really does resemble this global conformal primary operator. However, if you've ever studied 2D CFT before, you would know that having a conformal weight, delta, which is some operator rather than some number, like 7/2 or whatever, this is deeply weird from the perspective of 2D CFT. This is an extremely strange thing. I've certainly never seen this before. And in our case, it actually signals that we're working in the wrong basis. And what I mean by this is that these annihilation operators are in some momentum eigenstate basis. And the fact that their conformal dimension has this weird structure means that we shouldn't have been working with momentum eigenstates in the first place. We should have been working in a basis which is better suited to make these things genuinely look like global conformal primaries. Okay. With this in mind, I'll erase this definition. And I'll replace with it a new one. So we define a global conformal primary operator. We define this thing on the celestial sphere. We define this with an integral transform, which is known as the Mellin transform. So specifically, we have this following extremely important equation. O delta CZ bar is given by this integral acting on the annihilation operators in the momentum eigenspace. Okay. Now, specifically, one can compute the following, and this computation I will do on the blackboard because it's short and extremely important. So one can verify the following, that the commutator between L naught and O delta ZZ bar, well, the first thing I do is just rewrite O delta ZZ bar in terms of the momentum operators, the annihilation operator in momentum eigenstates. Okay, so that's the very first thing I want to do. And then I substitute in this equation here. Okay, so I have the same integration as before, but when I substitute in this equation, I find 2z partial z minus omega d omega. And this acts on the annihilation operator in terms of these momentum variables. And now what I do is I can freely integrate this by parts. So I have this omega d omega, and I just pull this over to act on the kernel of the integration. And the upshot is that we have the following. So the result of the integration by parts is that this thing now looks like this. And so I may pull this outside of this Mellin transform. And we just note that the Mellin transform of this annihilation operator is by definition this O delta ZZ bar. So we have the following. 2z partial z plus delta O delta ZZ bar. And if I hadn't erased this last equation, you would see that this is the correct commutation relations for a global conformal primary of conformal dimension delta and spin 0. Okay, and if you do the rest of the commutators, you'll be able to see that O delta ZZ bar is indeed a bona fide conformal primary operator with conformal dimension labeled by this parameter and spin 0. Okay, so far we've been studying the case where this A omega ZZ bar is the annihilation operator for a spin 0 particle in the bulk space-time. And it turns out that the boundary operator is spin 0 as well. Now, one can show the following fact, that if A omega ZZ bar is the annihilation operator for a bulk particle with helicity H, then if you take the Mellin transform of this to get this boundary operator here, then this boundary operator will always have dimension delta, and it will always have spin equal to the bulk helicity. Okay, so that's a non-trivial thing that one can show. Great. All right.
What is the inverse to the analysis?
Very good. Yeah. This is known, and let's see if I can do it live on the board. This is subject to errors, this equation, because I forgot to write it down. But the inverse of the Mellin transform looks like something d delta well, it's yeah.
But how can we interpret like a Fourier expansion? You know that there is like some Flywave expansion, or there is
Right.
But here, is there some simple intuition? What is Mellin transformation? I mean, some kind of you can think of it like a mode expansion.
Yeah. And I think a fair answer to your question is that previously these were written in terms of momentum eigenstates, and doing the Mellin transform rewrites their wave functions in terms of boost eigenstates. So this is a kind of funny thing to do, to be scattering in some boost basis. If there's time later on in this series of lectures, I'll show you how this works in a more concrete way. But celestial CFT is basically looking at scattering amplitudes in this boost basis. Fair enough? All right. Yeah, it's good that I didn't try and write this equation. All right, let me follow up with a question of my own. For what values of the conformal dimension delta is O delta an operator in the CCFT? And this is essentially the question of what is the spectrum of the CCFT? Okay, well, again, this is a little bit of a muddy thing because the field is so young. It's known that when you choose the conformal dimension to be equal to 1 plus I lambda for lambda in R, then this set of conformal dimensions, this is a complete set of operators. Okay. And what do I mean by complete? It's complete in the sense that a bulk particle in a momentum eigenstate can always be reconstructed from these via the inverse Mellin transform. Okay, so this is a good definition for the spectrum of operators in the CCFT. It's just these conformal primary operators where you choose their dimensions to be all things which live on this line. There's a little bit of a problem here. It turns out that the bulk translation generators their action on global conformal primaries defined in this way is to send delta to delta plus 1. So the upshot is this so-called principal unitary series it's closed under bulk Lorentz transformations, but under the full Poincare group, which has these momentum operators, it's not a closed subset of the complex plane. So this is it's a little weird, but it's ultimately not. It's not doomsday scenario. And the reason for this is because one can construct these weight-shifted operators still in terms of various functions of the things on the principal unitary series. Okay, so this is still a nice complete set of operators, but it's definitely unsatisfying that you have some symmetries of the bulk theory which are manifested in such a crazy way on the boundary. A possible resolution to this problem, and this is very much new work. There's been 2 papers that both have come out in the past year, so we're at the cutting edge of the field, is there's some evidence that choosing these conformal dimensions to live in integers, to either be all integers or all negative integers or something like this, there's some evidence that these are spanning. So instead of needing to use this complete set of operators, one could also use this complete set of operators. And there's a lot of very serious mathematical machinery about why this is a reasonable complete set of operators. But one notices that it has this nice property that it is closed under bulk translations. So if you're some integer before and then you apply the bulk translation operator, then your new conformal primary also has some integer dimension. So that's fair. Another reason that this might be a good thing to do, or something that you would hope to see, is because, as we'll see in the next 2 lectures, conformal primary operators which live at these integral values of the conformal dimensions play a very special role in celestial holography. In fact, they're related to currents and symmetries of the celestial CFT. So it would be nice to see them play such a fundamental role in the spectrum theory. But anyway, I'll leave my pontificating on this point to later.
So this constrains the values of the lambda.
Yeah, so lambda could be all real numbers. So in the principal unitary series, the spectrum is as follows. For every massless particle, you have a conformal primary operator, and you need to allow all dimensions of that conformal primary operator in your spectrum.
I mean, in the second case, where
Good. Yeah. So in the second case, you have to allow all integers, or perhaps all negative integers. Again, this hasn't totally been sorted out in the literature. Yeah. So either this set here is gives your spectrum, or the integers give your spectrum, or at least they're an over-complete basis. They're at least spanning. Okay.
I mean, you still haven't told us what this is to do. I mean, the S matrix is some mapping, right?
Very good, yeah.
You have preempted.
Sorry, if I understand, you just labeled in and out states in a clever way so far, right?
Correct. Yeah. So here is, yes, very good. So we want to write the scattering amplitudes in a way where the boundary conformal symmetry is manifest. So we want to be using this new definition for the conformal primary operators. So we can't work with momentum eigenstates, and we need to work with these boost eigenstates. And I'm going to give you the following definition. First, I'm going to write a scattering amplitude in momentum space as follows. So the scattering amplitude is parameterized by this momentum space kinematics. Is parameterized in terms of these omega, z, and z bars. And this is just a point of notation. I'm going to write the scattering amplitude in this way. So this is the n particle scattering amplitude. Okay. And these are now all annihilation operators acting on the outstate Minkowski vacua. And I can write scattering amplitudes in this all-out formalism using crossing symmetry. And that's what I'm going to do, just to make the notation a little bit simpler. The celestial amplitude this is defined by scattering not momentum eigenstates, but boost eigenstates. So we have this following very important equation. I'm gonna write A tilde for the celestial amplitude. And this thing depends on the conformal dimensions of the various operators, as well as their positions on the celestial sphere. And I'm just going to define this to be scattering these operators. Okay, these conformal primary operators. And we see that this is related to the usual amount, the usual momentum space scattering amplitude by Mellin transforming all the external lengths. So here's kind of the crucial idea which lives, oh, please.
So here the amplitude we define is at the level of a two-dimensional CFT.
You will see, ultimately, this is supposed to be something that one can compute using 2D CFT technology only.
Yeah, because I was wondering, could this CFT, as far as I remember, you cannot define an S matrix.
Very good. Yeah. So this celestial amplitude is defined as the scattering amplitude of not these operators in the 2D CFT, which you're quite right. You can't define an S matrix in a usual CFT, but the scattering amplitude of these kind of integrated momentum space operators. So this is the scattering amplitude that you would compute in 4D bulk space time. I guess maybe another way to say it is that you define the celestial amplitude literally as a Mellin transform of the momentum space amplitude. Maybe that's a fine definition. Yeah, this scattering amplitude, you like if you want to compute something like this, you always need to compute it in the bulk theory.
So how did you define the vacuum?
Just the usual Minkowski vacuum of the 4D bulk theory. So this is just the usual scattering amplitudes technology, but instead of scattering momentum eigenstates, which you're familiar with, I'm scattering boost eigenstates in the bulk quantum field theory. I guess that's all. That's all I want to say. However,
Sorry, I have a question.
Yeah.
This vacuum will be annihilated by the generators of the SL2C.
that's quite right. Yeah.
So they still not, are they not also the vacuum on the CCFT which in which these operators live naturally?
I might be a little careful before saying something like that. I guess the idea is that the vacuum state of Minkowski space is supposed to, I guess, be interpreted as the vacuum of the CCFT. But for reasons mentioned earlier, you shouldn't think about scattering amplitudes and stuff like this. But maybe this is the vacuum state in the language of the state operator correspondence and things like this in the CCFT. Maybe that's a fair way to think about it, though. Yeah.
If I don't act only on the outstate, I just get some conjugate operator instead, something like this.
Good. Yeah, very good. Yeah, so there's a similar definition. I guess you could call this dagger.
Basically do this, right?
Yeah, very good. And then now you have some daggers floating around in here, and that's fine. Great. Okay. Now, maybe this is so important. I'll write it over here. The idea is that because O delta ZZ bar, these were constructed to be 2D conformal primaries. It follows that the celestial amplitude transforms like a conformally covariant correlation function. And recall maybe from your readings of the Yellow Book or some other studies in 2D CFT that conformal covariance highly constrains the form of correlation functions that you can get in a conformal field theory. So for this reason, we'll often write the celestial amplitude just in this way. As this correlation function, forgetting about any bulk Minkowski vacuum. So this is how I'm often going to write the celestial amplitude as some correlation function living in the celestial CFT. All right, great. So this is mostly the end of what I wanted to say, but I prepared some bonus material, which is non-essential. So if there's any questions about how one defines celestial amplitudes or something like this, feel free to maybe ask them now.
So this A tilde transforms like a correlation function, but it's not a correlation.
It's a correlation
It
function.
should satisfy the word and entities of the,
That's right.
but it's not exactly a correlation.
I mean, it transforms like
Yeah.
that, right? It's not necessarily like in a unitary theory, right? Because maybe you have complex operative dimensions. I think the question is, can you understand what that CFT is if it exists?
That's exactly it. That's exactly it. Yeah. So the goal of the next few days is, and this is an ongoing problem. Well, an ongoing problem is to try and construct this from the top down. So, and by this I mean, you give me some CFT data, you tell me the spectrum of the operators, you tell me their OPE coefficients, and then you compute correlation functions here, and then you invert the Mellin transform, and you find miraculously that this gives you momentum space scattering amplitudes of some quantum field theory. So this would be the ultimate hope of celestial holography, or to do this for something that resembles our universe, is to find whatever structures of a CFT that live on the boundary, and when you invert the Mellin transform, they tell you about real particle physics that you can go and measure. So this is a very optimistic goal.
But I mean, if I take like a minimal model, take the Ising.
Good, yeah.
What do you get, right? You get some non-unitary S matrix.
It's a great question. I thought about this for a moment. Ising is a pretty bad example because the weights don't live anywhere like this. So there's, for Ising, I guess there's, or for all minimal models, there's a finite number of Virasoro primaries. And so you can't really invert the Mellin transform with this technology. So you really do need specific properties of the spectrum.
For a compact boson, is that
Has this been studied? This is,
I'm trying to remember. I think if I pick the radius right, I think I should be able to get all the feet maybe.
that's right.
I'm
Yeah,
not sure.
that seems very possible. I bet you for a compact boson, it'll be a little trivial because the OPs are just going to be determined by Wick's theorem or
Yeah.
something like this.
For a measurement of Witten model,
Yeah, for WZW, there are
Go
certain.
down the list.
Yeah, well, yeah, I guess that's fair. It's like all the rational CFTs are all the ones with like, you know, with things like this, the ones that we really have good access to. For WZW, there's certain structures in WZW, like the Katz-Moody algebras, which do appear in CCFT, and we'll see this tomorrow. So there have been some claims of you take some Liouville theory and then you couple this to some Katz-Moody algebra, and this reproduces some features of gluon scattering amplitudes in the bulk space. So this is a pretty optimistic goal, but there has been some work in this direction, yeah.
So it's like a deceptive service, the strong and weak coupling ratio.
Yeah, let's think. I wouldn't totally characterize it in that way. I guess weak coupling in the bulk means that you can do some sort of perturbation theory to compute amplitudes. But for the celestial CFT, there's been some proposals that you should realize that it's some large N limit of a certain class of theories. But I don't know if there's exactly a strong weak coupling where you have some coupling that you can actually dial in the celestial CFT, which is somehow inversely related to whatever couplings you have in the bulk. It's yeah.
Good question. If you have if your bulk theory has Berthollet's complementarity, how does that translate into?
That's a great question. Yeah, and Jungi asked me this just yesterday, and I didn't have a very good answer, so I probably should have prepared. Let's see. There are certain constraints on celestial amplitude from like very amplitude bootstrap perspective. So one assumes that amplitudes in quantum field theory, they're unitarity, they satisfy unitarity, what's it called? They're analytic and stuff like this. And one might ask, how is this behavior manifested in the celestial CFT? Recently, there's been some work in 2 dimensions. So I said you can run this story in all dimensions. And in 2 dimensions, the S matrix bootstrap is really well understood for bulk quantum field theories, but it gets a lot more thorny in other dimensions. The answer of how unitarity in 2 dimensions is manifested in the celestial CFT is somehow that all these correlation functions are real. They're not complex.
Sorry, there's no celestial sphere, right?
Very good, yeah. So in 2D, the celestial sphere is just 2 points.
Yeah.
So again, you don't have any ZZ bar dependence, but now you do have dependence on these conformal waves. And it turns out that if you compute the correlation function of whatever 0-dimensional celestial CFT is, you'll find that unitarity imposes that all these numbers are real. Okay.
So, the symmetry of the 2-dimensional CFT are somehow related to the 4-dimensional system.
Good, yeah, exactly.
Yeah, I mean, for example, what about if you have discussed about integrability? Many of most of the CFTs are somehow integrable. It means something about the system in 4 dimensions.
That would indeed. I would say that you probably wouldn't hope for integrability in a celestial CFT, which describes the real world, because you know that the real world isn't integrable. So constraints such as integrability, these many things like this would imply a similarly infinite set of constraints on. It would probably make the 4D theory integrable as well. So I would say that although you mostly understand 2D CFTs, which are integrable in some sense, the holographic CFTs, these candidate CFTs, are much less understood. Kind of like the holographic CFTs for ADS, right? There's some conditions on the spectrum and something like this, but it's very hard, or maybe you just can't hope to write down what one is. There's some large central charge limit, blah, blah, blah. And you can't actually, no one's actually been able to write down an example. So it might be a similar case where it's not going to be one of the conventional CFTs that are kind of like obvious rational CFTs or something like this.
The reason I'm asking is because you said about low scattering, you related somehow this.
Yeah.
Low scattering, so I was wondering about the speed or maybe a system about the conformal window.
Good, yeah. Yeah, this wouldn't be beyond what you could hope to say, but just because it's a young field, it hasn't been said yet. So maybe. Okay. How much more time do we have? Can I talk about this bonus material or no?
Maybe you can spend 20 minutes more.
Oh, perfect. Okay.
Can I ask you a question?
Please.
Have people thought about what if I have supersymmetry? Is it understood how 4D supersymmetry turns into 2D supersymmetry?
Very good. Yeah, very good. So it turns out that 4D supersymmetry doesn't obviously turn into 2D supersymmetry. The 4D supersymmetry algebra gives you some super BMS algebra in 2 dimensions, but it's not obvious that global supersymmetry turns into supersymmetry on the celestial scale. And this is some direction that I'm currently working on. So the story is still out there, but studying supersymmetry and celestial holography is definitely an interesting and relevant thing to do. Yeah, and the goal is to figure out how something like bulk supersymmetry implies boundary supersymmetry, but that's unknown as of yet. Massive particles, here we go. We're going to do this momentum parameterization story again. So the momentum of a mass m particle is conveniently parameterized as follows. P mu is equal to m over 2y, 1 plus y squared plus z, z bar, v plus v bar minus I, z minus z bar, 1 minus y squared minus z bar. And you'll find that this satisfies the correct on-shell relation p squared is equal to minus n for all values of y, z, and z bar. The corresponding conformal primary on the celestial sphere is this is given by the following integral transform. So it's now no longer the Mellin transform. You now integrate against some Green's function, which has the conformal dimension delta encoded in it. Okay. So now here's our annihilation operator for the massive particles parameterized by y, w, and w bar, and you integrate against some Green's function. What is this Green's function? Well, this Green's function is precisely this. And you'll notice that this is the bulk to boundary propagator in ADS3 CFT2. Okay, so somehow this structure appears naturally in ADS CFT, and this is maybe one of the ways that celestial holography is kind of related to this. The idea is that celestial amplitudes they're now defined as follows. You integrate massless external legs against the Mellin kernel. And you integrate massive external legs against this new integration kernel G delta. Okay? So an exercise is show how in the massless limit this momentum parameterization P mu converges to the massless momentum parameterization I've given earlier. So this massless limit is going to be m goes to 0, y goes to 0, and there's going to be some ratio of the two, which is remaining finite. And a related exercise is to show that in this limit, this integration kernel, this bulk to boundary propagator, this just gives you the Mellin kernel. So I could have started this whole discussion talking about massive particles only, and then I take the massless limit at the very end. But certainly the Mellin transform is a bit easier to see than this. So that's why I did it the other way. But this allows you to define celestial amplitudes when the external particles in the 4D quantum field theory are massive as well as massless.
And if I have this operator O delta, how do we know that from the point of the celestial CCFT, how do we know that it comes from the massive or massive?
Very good. It's hard to see, obviously. And not a lot of people have thought about massive particles because there's a lot more integrations that one needs to do. So I don't think there's an answer in the literature, but optimistically, one might hope to see this in terms of things like OPE coefficients. So maybe the mass of something appears universally in some OPE coefficient with the stress energy tensor or something like this. That's something that one could optimistically hope for, which would tell you that O delta is really a massive particle in the bulk quantum field theory. Maybe.
Another question is here probably this conformal generator acts nicely both. I mean it's the same as this conformal generator when act on the O. It's the same as act on this.
Yeah, exactly. So these LNs, when acting on O, will tell you that O delta is a conformal primary.
Yeah, that ejection with the free gas, like a free gas ray in the Mellin, it's very easy to see that how this
right.
Operator act on the A translate O. That this is also true.
That's right. It is also true, but it's an exercise for sure. Yeah.
Another minor thing, is there any problem in that integral? Like usually this is related to this H. It looks similar to this HKL, the construction of this bulk operator from the CFTs. I'm not sure it is, but that usually that such kind of integral sometimes it has a problem, like a diverse, but I just wonder whether this integral is well defined or maybe it's.
I haven't heard of any issues, but let's see.
Maybe it's okay. Maybe the HKL, maybe black hole case, maybe problem, maybe. Yeah. Anyway, so
This is the usual story for ADS3 CFT2. So I think you're pretty safe.
another question.
Yeah.
In the massless case, I can kind of think of this parameter omega as being related to, you have to say where on stripe plus your particle hits.
Right. Good.
But what is y? Because everything here has to hit I future, right? So
Very
what
good.
is y physically?
Yeah, terrific. That's an excellent question. Okay. So I have my Penrose diagram, and what I'm going to do is I'm going to split it up into 4 quadrants, kind of like this, and I'm going to foliate this top quadrant with 3-dimensional hyperboloids. Okay. And as you mentioned before, all massive particles, they start at minus time like infinity, and then they go through the geometry, and they always hit here. However, they hit the hyperboloids at some place, and I'm going to choose this parameter tau to be running across all these hyperboloids. And somehow as tau goes to minus infinity, working with these hyperboloids essentially resolves this singularity. So although all the massive particles hit I plus, they'll reach I plus passing through a very well-defined trajectory on these hyperboloids. So as we send tau to infinity, they'll asymptote to a particular place on these hyperboloids, and that's how you should think of resolving this singularity. And the place that they asymptote to on these hyperboloids is related to z and z bar, which is what makes these well-defined operators on the celestial sphere. Perhaps another way to think of it is that these are in boost eigenstates, so there are infinitely many boosted. And so when you really boost a massive particle, it almost looks as though it was massless. So that might be a qualitative way, although maybe less precise. Great question, though.
Yeah, but actually my question, what my confusion is that in this preview, this y, z, z bar, they are momentum space variables.
Right.
But here you are talking about position space Penrose diagram. So
Very good.
how do these two get related?
Great, yeah. Well, maybe I shouldn't. Anyway, we don't need it. So the most obvious classical thing that you can do is just say that the world line of a particle, x mu as a function of tau, is something like some initial position, say it moves on a geodesic, and then it moves on some straight line trajectory. So it looks like, I think, tau over m p mu. So this is what the straight line trajectory looks like in this geometry. Okay. And in this way, you tie the momentum space variables, which tell you what your p mu is, to the position space variables. Now, when you do scattering amplitudes, you're considering either some wave packet or you're considering some momentum eigenstates where they're not just a single, where you're not just following a single geodesic. But again, the story is very similar where the whole wave packet is resolved by a particular point on the hyperbola. And these hyperbolas being H3, this is essentially what gives you the bulk to boundary propagator in ADS CFT. So we have Euclidean ADS, which is these hyperboloids, and the celestial CFT kind of lives on the boundary of these hyperboloids. And so that's why we need the bulk to boundary propagator. With what little time I have remaining, I hope to do, oh yeah, please. Oh yeah, very good. So now the spectrum is 1 plus I lambda, where now lambda is positive. Okay, so now you don't have all negative lambda, but somehow the principal unitary series for massive things is just the positive ones. It's just some mathematical fact. Yeah. Let's see. It's a very good question. It's a very good question. Somehow when you send the mass of some particle to 0 in the CCFT, it often isn't a very smooth thing that you're doing. We'll see certain soft theorems and asymptotic symmetries next time. These are associated to massless particles in the bulk. Massive particles in the bulk don't have these things. And these features are manifested very naturally in the CCFT. So somehow taking the massless limit in this CCFT, although it seems innocuous, it can kind of be a little severe. And I think this is just one example in that, but it's a great question. It's a great question.
These results are this shift in delta for translation.
Yeah, exactly. Yeah. Yeah, these would suffer a similar problem. All right, let me finish with one last example. I'm going to consider the simplest scattering amplitude I can possibly imagine, which is a 3-point tree-level scattering amplitude between a massive scalar and 2 massless scalars. So in momentum space, this scattering amplitude is just equal to the following. And the hope is that I will compute the celestial amplitude for this. And it's actually not terribly difficult. So the celestial amplitude is given by the following integral transform. D omega 1 over omega 1, omega 1 delta 1, d omega 2 over omega 2, omega 2 delta 2. This is me doing the Mellin transform on the massless legs. And then for the massive leg, I need to do the following integral transform. dw squared dy g delta. And the thing that I'm integrating against is just a delta function. The fact that it's a delta function means that we can do many of these integrals rather immediately. Okay. So let me just explain how one would do this. So there are 5 integrals to do, and there are 4 delta functions. So we can do some of these integrals immediately. And the ones that are best to do immediately are y, w, w bar, and then omega 2. And then when you do these integrals, you're just left with a single integral over omega 1. And it turns out that the remaining integral is just a beta function. Okay, so that's not so bad either. And one finds the following, that the celestial amplitude is equal to it's equal to the following 3-point coefficient over these conformal factors. So the 3-point coefficient depends on which values of delta we choose. But already we see that this is the structure, the most general structure allowed of a 3-point correlation function, the most general structure allowed by conformal invariance. So we know that conformal invariance in a 2D CFT fixes 3-point correlation functions to be precisely of this form. So it's already nice that we see this coming out of a concrete computation, though it was of course guaranteed to be true.
So this is just for this tree level.
Very good, yeah. And what is this 3-point coefficient? Well, it's G, this coupling, this sticks around. And then we have minus M, where M is the mass of the massive particle that we're scattering, raised to the power 2 delta 2 plus delta 3 minus 4, divided by 2 to the power delta 1 plus delta 2 minus 1 times the following beta function. Beta function delta 1 minus delta 2 plus delta 3 over 2 delta 2 minus delta 1 plus delta 3 over 2. So this is a celestial amplitude for this most simple example. You can totally do the computations, and it gives you a structure that you're very familiar with, and we're pleased to see. All right, any final questions?
I mean, this is tree level, right? I mean, I can have thresholds, I can have cuts and stuff, and in general for one function. Is this just gonna boil down to this specific function C?
Yes, that's right, it will.
Because I mean, the Z dependence, I guess, there's no choice, right? It's
Good.
completely kinematically fixed, but that means that secretly all of the physics is in this function C.
That's quite right, yeah.
And also, I guess there's some subtlety about what are the ranges of delta or something.
Yes, exactly. But that's exactly right.
But so is it known? I mean, if I can have some loop and then there's a cut when something running in the loop becomes on shell.
Yeah.
What is that? Do you know where those types of kind of structures and amplitudes turn into here? Is it known or no? And I can similarly, in a related question, I can ask about like the optical theorem. Right. What does the optical theorem mean for celestial amplitudes?
This may be known, but not known to me. Yeah, but I think on that this evening and try and come back to you. No, because that's a very fair question, and the particular contour that you choose, it's not like a God-given thing. If you choose any other contour for the Mellin transform, then O delta will always be a conformal primary. So you can choose a compact contour and things like this. So it's a good question, how branch cuts and stuff that appear in amplitudes are dealt with in this framework.
So say that again, like contours.
Yeah, good. So if I define O delta to be d omega omega like this, I can specify any contour C, and this will always transform like 2D conformal primary. And the reason for this is because if we remember our earlier derivation, I just hit the L generators on here, and then I do an integration by parts. And the integration by parts is fine for all these choices of contour. Okay, so that's kind of the idea.
What does it mean?
What it means is that the choice of contour isn't obviously just 0 to infinity. So you don't obviously just have to integrate omega from 0 to infinity. There's some works where you consider some closed contour centered about the origin. So you actually do some contour integral to define the celestial operators. And this is useful when talking about celestial operators at integral dimensions and talking about soft theorems and things like this. There have been some papers which use this compact contours. So again,
These are like different sources of origins or some definitions within the same area, or are these different areas?
it's very good.
And how do I like associate contour deformation in the massive spectrum, the massive spectrum, and
Yes.
the body contour and the shadow contour?
Yeah, so to answer your question, most papers choose one particular choice of contour. However, if you know, I said these amplitudes are analytic, so they satisfy some certain analyticity behaviors. And one can often deform these contours, so one can deform this semi-infinite line contour to be precisely this. So if one assumes some fall-offs on scattering amplitudes and this kind of behavior, then one can do this contour deformation and relate them to one another. So that might be a fair question, but it's definitely something, you know, you need some analyticity assumptions and fall-offs and blah, blah, blah. Yeah.
Any other question? Let's again. So let's resume at 4 p.m.